The most difficult thing is the decision to begin. The journey of 1,000 miles commences but with a single step.
Change is involuntary, but growth is intentional. With tenacity, we have continued this journey, and we shall keep walking, steadfast and steady.
Good morning, everyone. I am Nalanshi, and this is Atharv, and we are the hosts for this ceremony. Today, we sit here to celebrate the 13th Foundation Day of IISER Pune. Almost 2 decades ago, a journey began, and we have made immense progress in this time.
Chief guest, Professor Sandeep Trivedi, all the faculty members, students, and staff. This day is to celebrate the support and contribution of everyone who has shaped our institute into the haven of science and teaching that we see today. Now, I would like to invite the director to present his report and carry the ceremony forward.
So I'd like to begin by welcoming all of you to this 13th Foundation Day program. So welcome, and it's a great pleasure to have Sandeep Trivedi as our chief guest today. I'll talk about him a little later, but it's really a great pleasure. I've known him for many years, heard about him well before I met him, and he's really one of the most distinguished physicists in the country. But my job right now is first to give you a summary of what's been happening at the Institute over the past year or the past few years. And there are people here, including our chief guest, who don't know as much about IISER as we all, others of us do. So let me start off by presenting a report on IISER and its activities over the past year or so. So, okay. Hopefully this will work, yeah. So it's our 13th Foundation Day, and what has happened in the past year or two is we have launched 2 new departments, one of data science and a Department of Science Education, which is really yet to take off. Data science has barely taken off, and we have faculty members distributed now over 8 departments, working in many different areas of science and also the humanities. As many of you know, I believe humanities are an important component of an education, and I hope the humanities department does also grow well in the next few years. So we have had new faculty members joining in the past year. In chemistry, we have Devanshu Sil, and in physics, we have Surabhi Jaiswal. And there have been several visiting faculty members who have joined, who are listed out here, emeritus faculty who have also joined in the past year, and also guest faculty members, especially in data science, who have been associated with the Institute in the past year. So with this, we have roughly 137 regular faculty and a set of visiting and guest faculty as shown out here. We have now roughly 1,700 students, and so we have the scope to hire another 30 odd faculty members, and hopefully that will happen in the next year or 2. So the Institute has been doing well in science. In this past year, we have had a large number of publications, most of them of high quality. And the cumulative number is now nearly 5,000, and maybe by today it's exceeded 5,000. Patent numbers have also increased. We have now quite a large number of patents for the Institute, which is very good. And hopefully over the next year or 2 years, uh, there will be more and more faculty members who try to translate their research into goods or into activities which are good for society and for themselves. Um, the number of grants has been remaining roughly constant at the Institute at 45 or so over the years, and really contribute the major fraction now of research expenditure at the Institute. Faculty members have been doing well. So we've had Deepak Dhar, an emeritus professor who got the Padma Bhushan, our former director K.N. Ganesh got the Padma Shri, and Shabanti got a SERB Power Fellowship. Sujit was named a Fellow of the Royal Society of Chemistry and also got the Bronze Medal of the Chemical Research Society of India. Kalka was elected as a Fellow of the Indian Academy of Sciences in Bangalore. Ramana got the Wildlife Service Award. Maumita got a Humboldt Research Fellowship. Deepak also got the R.D. Birla Award. Venkateshwar Pai got the Mahakavi Kalidas Sanskrit Rati National Award. Richa and Nixon got senior fellowships of the Wellcome Trust, DBT Wellcome Trust Alliance. So we have had good support from the government over the past year, even though the financial support came in fits and starts and led to us not being able to plan things as well as we would have liked to. But finally, as all the faculty would know, we got sufficient funds for the year. So we have had good support from the government. The Minister of Education visited us last May. He laid the foundation stone for the space for the Department of Data Science, and also inaugurated the National Facility for Gene Function in Health and Disease. That's what the Animal House is called. So we have had several new MOUs, agreements with bodies. I think one which is very important and hopefully will lead to our association with one of the premier social science humanities institutes of the country, the Tata Institute of Social Sciences, is to have a joint program with them which will fructify only after various components have to be approved both by them and by our Senate. But we want to do things together. So we have had international partnerships. An important one is the one which has going to be implemented soon with the Johns Hopkins University, with the University of Notre Dame, and also with Leibniz University. Our endowments cell has been under the stewardship of Kundan, and also Santanam has been especially active, and they're getting a lot of money, and much of it comes at the last minute, and we have to figure out how to spend it within the financial year. But hopefully we will have very soon a protocol for handling this much better. We're getting more money than we expect at the end of the year, and it becomes difficult to deal with that. So we get travel grants from various agencies, we're getting support from various companies in many different activities which the Institute is engaged with. And what's very nice is that we're getting money to financially support students. We have a problem, of course, of supporting students who finish 5 years as PhD students, students who come from underprivileged backgrounds and come from economically backward, societies, and we are trying to provide as much as financial support to them as possible. Students have been doing well. There's a lot of student activities, a lot of clubs on campus. One of the important activities is the conduct of a quiz called Mimamsa which just was concluded just a week ago. This is an all India science quiz where many universities, institutes from all over the country participate, students from there participate. The questions are such that I'm generally not able to answer any of them. And it's a tribute to our students who formulate the questions with the help of our faculty and come up with rather difficult questions. But students do well in these. IISER Pune doesn't take part because of conflict of interest matters, but the top institutes of the country do, and it works very well. Disha is an organization which works with underprivileged people, underprivileged students, and it's a really commendable activity on the part of many of our students. Students are also doing well in other activities. There are startups now at our Atal Incubation Center, which are essentially student startups. There are 2 of them, and hopefully they will do. They'll become rich and famous and then support the institute very strongly in future. So we get good students at the PhD level, and several of them have got the PMRF, the Prime Minister's Research Fellowship. We need to get more, but there are limits to the number we can take because of some, I don't know, the IITs don't have some way of limiting students at various places. Other students have also done well at various competitions. The OFSA competition by the DST, students have done very well there. There's a competition called iGEM, and it's for biology and biotechnology, where students come up with some novel experiments, novel designs of important in biotechnology. 2 of our student teams participated, both got gold medals, and 1 made it to the top 10 of the undergraduate teams. So these teams also work under the tutelage of faculty members. Our sports team, as many of you know, I consider sports to be really very important in an educational institute, have been doing quite well. They were second at the Inter-IISER sports meet held a few months ago. We had a large team going out there, and they came second overall amongst the 8 teams which participated, which included 9 teams, including IISER and the Indian Institute of Science. So the institute has, for many years, carried out a lot of outreach activities, and it's a tribute to our faculty members that they participate strongly. They design various programs. They initiate various programs with external funding. And we have a very active student activity center where school kids mainly come and experience science by playing with science toys. And we have a very large number of students coming in to our science activity center every year. We have a science media center which has also been doing well. Its documentary on G.N. Ramchandran won a prestigious award, and it has been engaging with various bodies inside the institute as well as outside, helping them, for example, in NPTEL recordings, etc. One of our principal outreach programs right now is called IISER. It's a collaboration of IISER with 4 other organizations, including DST, the Tata Technologies, Tata Sons, the British Council, and I'm sure I'm missing a name. But it's something which we are very proud of, and is leading to, hopefully, better capacity of teaching at the college level in various states, including Bihar and Uttarakhand and Maharashtra. We have also teamed up with the Maharashtra state government. They're quite keen also to improve college education in the country, and they've set up an academy in Pune itself, and there's a program where we are engaged with teachers throughout the state, as you can see on this map. In addition to our departments, we also have a center, a very important center, the Center for Water Research. This is headed, well, that's not that important, but Bijoy heads it right now, and he's done a great job in getting faculty members on campus interested in research connected with water. We all know that water sooner or later is going to be a very big problem in the country, having good water. And this is something which it's very important that the institute continue doing this for both the city of Pune as well as for the country at large. I'm hoping the slides are long enough for you to quickly read them, so I'm not directly reading them. So we have 2 Section 8 companies on campus. One is the IISER Seed Company. It's basically called Seed. And it's been doing quite well. It's got a large number of startups now. And they're somewhat limited in space, and they keep pushing for more space because they have more and more people wanting to come in. And hopefully the institute will be able to provide them with the space they deserve. So it's really doing well, and hopefully will become one of the major startup incubators in the country. We also have a new Section 8 company. I always get mixed up in the name here, but iHub Quantum Technology, QTF. This is something which was started recently. A dozen faculty members in the physics department got together to write this large grant, and a company called the QTF was established at IISER Pune. And the idea here is to develop quantum computing and other quantum technology at the institute. The institute acts as a hub, and also which funds research in this area at other institutes and universities. And I hope this activity also flourishes in the next few years. So the institute has been doing well. The rank is quite high. We would like to get to below 20. That's difficult for a small institute such as ours, but because the way the ranking is done is in favor of larger institutes, but hopefully we'll near 20 or go below 20 in the next 2-3 years. Other rankings, which may or may not be important, are also shown out here, and we're certainly doing quite well in these rankings. So with that, I come to the end of my report, and I think, yes, and my job now is to introduce Sandeep and have him give his lecture today on entanglement, or the entanglement frontier. So it's a pleasure having Sandeep out here. So Sandeep was a student at the Indian Institute of Technology, Kanpur, and I first heard about him from his sister Nandini, who was a very good friend of mine, and she told me about a kid brother who was acing everything at IIT Kanpur. And so it was not surprising when I heard that he went to Caltech for his PhD, and he was later a postdoc at the Institute of Advanced Studies at Princeton, and then at, I think, Argonne, or in Illinois. So he's done seminal work in string theory, in cosmology, in high energy physics. And there's a theory called KKLT. I believe the T must be Trivedi, which is a very famous theory. I don't know much about it, but hopefully he will tell us a little about it. And which has really made a big difference in our understanding of high-energy physics and cosmology. So he is a distinguished professor right now at the Tata Institute of Fundamental Research, and he was the director until a few years ago, and he's continuing now to do really very good work in cosmology, string theory, and high-energy physics. He's, of course, been decorated by with all the awards you would think he would be having. He has all of them, including the Bhatnagar, the Infosys, and various other awards. And he's a member of various academies, as you would expect. So it's a great pleasure having Sandeep here, and I invite him up to give his lecture. Sandeep?
Okay, well, thank you very much, Jayant, for that overly kind introduction. It's a great privilege for me to be here. Will they be able to hear me if I walk around? No, right? It's a great privilege for me to be here to participate in the Foundation Day celebrations, the 13th Foundation Day celebrations of IISER Pune. We have all watched in the academic community of the country with great hope the growth of this wonderful institution, and it's really a great feeling today, as Jayant told us about all your accomplishments. It's really a great feeling to see how far you've all come, how much you've achieved, and really I think we all look to you with great hope and promise for the future. This is one of these institutions we hope will really take India into the 21st century and continue to take us ever forward to greater heights. So really thank you very much for giving me this opportunity to be here today. And also allow me to say thank you very much, Jayant, on behalf of the academic community of the country for your stewardship of this organization over the past 5.5 years. It's really been a tremendous contribution for all of us in science in India. Thank you. So what I have today is a talk where I want to share with you some of the promise and excitement in a new field. Now, it's not a new field for many of you because Jayant told us about the quantum technology foundation you have all set up, and that clearly means that you're already on top of these events, these developments. But I still want to share this excitement with you all because I feel it in my heart. And it's so befitting to come to you on this occasion, to this institute of such promise for the future, and share one of the great, I think, exciting stories that are now beginning to unfold in physics in front of us. And this pertains to what I call here the entanglement frontier. Now, this is a new frontier of science. It does not pertain to some of the well-known frontiers which have been with us for some time. In particular, it does not directly, at least, this pointer is not working, okay. Here it does, but not there, okay. It does not pertain to the very small, directly at least, deep within the atom. That's a wonderful frontier. It continues to be one which will occupy us into the 21st century. You have established a great group in high energy physics, so you're very much a participant in that frontier. It does not pertain to the very large, way beyond our solar system, even our galaxy, the clusters of galaxies, and so on and so forth. That's a very exciting frontier. Pune is a center of that with NCRA and IUCAI, and I'm sure you all participate in that story as well. The entanglement frontier is something else. It does not pertain to the very many either. put together many atoms, you get, or molecules, you get new emergent behavior in condensed matter physics. Put together neurons, you get new emergent behavior. And in chemistry, you have emergence and so on. These are all very exciting areas, but the entanglement frontier is something else. So what is it? Well, interestingly, it pertains to our growing understanding of quantum mechanics, its true meaning and significance. Since quantum mechanics provides the bedrock for our understanding of science, this new frontier promises to have important implications for many aspects of science, straddling physics, aspects of chemistry, computer science, and various aspects of engineering and even mathematics. And so it's this tremendous confluence coming from truly understanding the fundamentals of quantum mechanics and how it pertains to both logic and our capacity of thought and the workings of nature. So here, this is a cartoon. At the center of it all sits the quantum principle and our growing understanding of it. Now, it might seem, I want to share some of this excitement with you today because, especially coming to an institute like this, because, I really think the next few decades will see very exciting developments in this area. And it's a wonderful contribution. You stand in this auditorium with Professor C.V. Raman's picture here, and if young people are going to make a mark in India, I think this is an area they can do it. Okay? So it's an area of great promise for young scientists and engineers, I think, actually, to make landmark contributions. Okay, now, it might seem strange, actually, at first, that there is renewed excitement in understanding quantum mechanics and its implications. After all, quantum mechanics is about a century old. Every undergraduate in IISER probably runs quantum mechanics in your first year or something, right? So, how can this be a new frontier of science? And the answer is that the quantum world is really strange. It is weird. It is so different from our understanding of the classical world, from which we draw our intuition, that it has taken us a very long time to slowly begin to understand it. It's taken us 100 years, and even today, we are only slowly beginning to understand how quantum mechanics works and its implications for how we might be able to, do new things with quantum properties and quantum technologies. Understanding it has not been easy. Well, here are two quotations for you expressing that thought. One is by Niels Bohr. Niels Bohr, as you know, was one of the real father figures of quantum mechanics. If anyone understood quantum mechanics, it would have to be Bohr. And this is what he says in 52. This is not anywhere near the advent of quantum mechanics. This is many decades after. And yet this is what he says. For those who are not shocked when they first come across quantum theory, cannot possibly have understood it. Here's another quotation. By Richard Feynman, another towering figure, and actually somebody who presaged the current developments I'll tell you about as to how understanding quantum mechanics could fundamentally change our understanding of how we compute, how we build computers. He was really ahead of that by several decades, and the world took that much time to catch up, besides, of course, doing absolutely seminal work, in fact, in setting up the basic foundations of quantum mechanics and so on. He says, I think I can safely say that nobody understands quantum mechanics. Now, knowing Feynman, what he was saying was, I can safely say I don't understand quantum mechanics, ergo nobody understands quantum mechanics, but it expresses the thought that it's very hard to actually understand this subject. So what I'm going to do today is tell you, at least briefly, what contributes to this essential weirdness of quantum mechanics, okay? What is it that makes it so hard to grasp? And in some ways, some of the key properties which we now believe will play a crucial role going into the future are tied to this property of entanglement, which was part of my title. And these properties were really brought to the fore in brilliant work done by John Bell, and it's summarized in what's called Bell's theorem, which I'll give you a bit of a glimpse on. Experimentally validating this theorem is one of the reasons why the Nobel laureates of 2022 in physics got the Nobel Prize. So I'll be able to touch on that as well. And then we'll go on to exploring this idea of how to make use of entanglement by briefly talking about quantum computers, building devices, and a little bit, every scientist wants to talk in the end about their work, so if time permits, a little bit about the work we've been doing in this area. And then we'll end with conclusions, but you will keep me to the time, right? Okay. So let's see how far we get. There are two essential reasons why quantum mechanics is so hard to grasp in our classical minds. Hunter-gatherer minds were not equipped to think about quantum mechanics or understand. The quantum description is intrinsically probabilistic, but it's even more subtle than that. It's not probabilities. The fundamental quantity is an amplitude called the probability amplitude or the wave function, out of which you build probabilities. There is no analog of this in our day-to-day experience. Okay? We do deal with probabilities all the time, but nobody is equipped, intuitively at least, I think, to deal with probability amplitudes. You acquire that intuition after years as a physicist, but we're not born with that. So here, this is the wave function. You have to take the wave function, take its absolute value, square, and out of that compute a probability, say to find a particle at some location. So the wave function is like a wave, that's why the name is given. And just like waves can, superpose on each other like water waves, you do that with the wave function. And then the physical effects are like the power or the intensity of the wave. You have to take the amplitude and square it. So here, it's like water, except this is a probability amplitude, okay? Takes different paths, interferes with each other, give you a net resultant amplitude somewhere, which gives you a probability to find, say, a particle, find a group of particles, or whatever are the degrees of freedom. It's a little bit like Young's double slit experiment, right? Every undergraduate probably in IISER does it in their first year. It's a beautiful experiment, done in 1801, by the way, by Young. Imagine, quite a brilliant piece of experimental work, changed our understanding of light, established the Huygens principle. But this is for light. You have two slits, S1 and S2, light goes through, you get a pattern on the screen, and we all know that the pattern arises by summing the paths of light from the two slits, allowing it to interfere on this screen, and then computing the amplitude and taking it square. Okay? So light interferes in this way, and the amazing thing is that the wave function does the same thing for anything described by quantum mechanics, including what we think are particles. And so here is the famous double slit experiment, now being done for electrons. You have a gun which is spitting out electrons. It's going through two slits like light was, falling on the backstop. And you calculate, you can march along the backstop with any detector and measure the probability of finding electrons. And what you get is this final interference pattern, very much like what you got for light. And this is an amazing thing when you think about it for electrons. If you block the second hole, number 2, you get the probability P1. If you block the first hole, you get P2. Keep both of them on, you get P12. And in P12, if you look carefully, there are places where there was more probability of the electron to reach if only hole 1 was open. And that probability goes down when you open the second hole. Now, classically, if there was some probability that the electron could reach somewhere on the backstop if it were allowed to go through the first hole, and you now allowed it to go through the second hole as well, how could that probability go down? Because there are more ways for the electron to do it if you were just adding probabilities. But experiment shows it goes down because you have to add probability amplitudes which interfere like light interferes. Okay? And so, that's the fact of life. You have to deal with this superposition. Okay, And classical mechanics, you have definite probability, you have definite positions. In quantum mechanics, we have the Heisenberg uncertainty principle, as you all know. These are all tied together with the fact that you get superpositions. Okay, one last thing and we'll go on. Of course, probabilities arise, as I said, in day-to-day life, but they arise in classical mechanics because you choose not to keep track of all degrees of freedom. For example, you throw a coin up. It's a very complicated process. The light the light interacts with air molecules as it goes up. And you have to keep track of exactly how you have hit it when you spun it up. If you don't keep track of all those degrees of freedom, then you're left with a probability of whether it lands up or down. But in classical mechanics, if you could keep track of every degree of freedom, there would be a deterministic answer. Of course, very hard to calculate in the real world. The quantum world is different. The probabilistic nature is intrinsic, not out of ignorance, but due to the fundamental properties of quantum mechanics. Okay, this is the first thing. This has been known for some time. You come to terms with it. You take first course, second course. By the end of your fifth course in quantum mechanics, you're equipped perhaps to handle it. But then there's something else. And it's this something else which has taken decades, literally decades, to kind of come to grips with, and which is what is driving all the excitement in the field. And I want to tell you what the second property is. It's called entanglement, and it's part of the title of my talk. And it's something truly very strange. And it has to do with the following. Physics is local. What locality means in physics is no signal can travel instantaneously. Every signal must at least travel with the speed of light or slower. So if I do something here and you're in the next room or you're in Andromeda, it's going to take you time to find out that I did something here. Okay? Effect, takes time after cause. And the amount of time is limited by the speed of light, which is the fastest signal which can travel. So physics is local. This is one of the great properties about our laws of nature. But it turns out, despite all physical effects being local, in quantum mechanics, our intrinsic description of the state is non-local. Okay, it's non-local. You cannot describe a quantum system just in terms of local degrees of freedom alone, although the final consequences are all local. This is a very strange kind of thing. There are inherent non-local correlations, it seems. Okay, now Einstein, such an amazing person, with his unerring instinct to put his finger on key physical aspects of reality, put his finger on this point. And in a very, very famous paper written with Podolsky and Rosen, he first brought out this weirdness of quantum mechanics. And it has been called since then spooky action at a distance. I don't like this word very much because Einstein, of all people, knew that you can't, action at a distance suggests instantaneous change. Einstein knew that couldn't happen. Einstein's theory of relativity forbid it. But he brought attention to this kind of non-locality in the description of a state. So I'll tell you what I mean by that. I got rid of it. Here it is. Just to illustrate, suppose you have two electrons or two particles. One is on Earth, the other, just to dramatize, is in Andromeda. And the full state, the wave function describing it, that state is given here. The state is what's called a spin zero state, right, in physics, which is a superposition of up and down spins, first electron up, second down, minus, first one down, second one up, for those of you who know this. Otherwise, it's a superposition of up and down in a kind of correlated way, which we are going to call entangled. Okay? The two spins are entangled here, colloquially, let's say here. One is up, the other has to be down. The other is down, the second one has to be up. Okay, like that. This is the state of the system. You can't describe the electron, if you're using a wave function, just in terms of its state. You have to use the properties of the other electron, no matter how far that electron is. Okay, no matter how far that electron is. This is very strange, Einstein said. He said, look, contrast this with what happens in classical mechanics. If you have one electron, let's say one particle here, the other in Andromeda or wherever, you would have the position and momentum of this particle. You would have the position and momentum of that other particle. Both are completely local. The full description of the system is just put together by putting together the positions and momenta of both of them. Okay? They interact with each other. Let's say this one jiggles, out goes the electromagnetic signal, it reaches the second particle, 2, etc. It feels the kick. It's all manifestly local. You have local degrees sending out signals which are propagating. Something very weird in contrast, he said, is going on in quantum mechanics. You have this bizarre state which looks non-local, and then we have to work hard and prove, despite this non-locality in our description, all signals are local. He said, why is this the case? If physics is local, then a complete description should be possible where everything is local. This non-locality for Einstein suggested to him that we didn't yet have a complete formulation of quantum mechanics. And his thinking was, maybe there are some extra local hidden variables, we are not keeping track of them, and that's why we are getting this weird non-locality. Okay? So that was the thinking. By the way, to illustrate this non-locality, it might seem at first that this is very strange. If you measure the first electron, this is often how it's said, and you get the answer plus, you know that the first electron is in the plus state. Say on Earth, you do the experiment, you instantly know, because the two are correlated, that the second electron in Andromeda is now in the down state. Okay? That seems very strange. How could that happen? I told you no signal goes propagating faster than light. And yet it seems to happen. But you have to think through the experiment carefully, and finally you get it. I won't do it here. Finally it turns out that actually no signal can go. And the reason it can't go has to do with the first aspect of quantum mechanics, probabilistic aspect, okay, which is if you had just one pair and you did the experiment, you would either get up or down. If you got up, yes, the electron in Andromeda is instantly down, but the electron in Andromeda doesn't know you've done that experiment. It just says, okay, once in a while, if I'm measured, I'm going to come out up or down, okay? So there's no actual transmission of information, because anyway things are probabilistic. So the two aspects, probability, amplitudes, and entanglement, mesh beautifully in a logically coherent structure. But Einstein wasn't satisfied. He said, but why should there be a non-locality in description if there isn't in physics? Now he was very troubled by this, but his objections were philosophical, because he acknowledged that there was no real conflict in terms of signals traveling faster than light. And so, his objections remained in the domain of philosophy. Most physicists were kind of derisive of it. It's okay. Physically, we know nothing strange is happening. Let's go on, explore the quantum world. And that's where things stood. Okay, for many years, that's where things stood until this brilliant work by John Bell. Now, you see, Bell's work happens in 1964. Quantum mechanics is invented at the turn of the century. Einstein's objections are already in place by 1930. It takes 35 years more for Bell to formulate this theorem, okay, which moves Einstein's objections from philosophy suddenly into physics. Because what Bell showed in his remarkable work, the other thing, if you're an undergraduate here, is this remarkable work is based on 4 lines of algebra. Okay, there is nothing here that even requires calculus. Okay, and yet I think it's one of the greatest advances in 20th century physics. Okay, and the reason this is possible is, again, because quantum mechanics is so hard to understand that if you can advance our conceptual understanding, you don't need fancy mathematics. You just need to have truly, truly understood it, like Bell did. What did Bell show? He showed that there was an experimental way to distinguish between the kind of alternative theories Einstein was proposing with extra variables and so on, from which this non-locality of description could have arisen, because we are not keeping track of all degrees of freedom. There was an experimental way of distinguishing between such theories and quantum mechanics. And he said, look, regardless of the details, if you have such a theory based on standard ideas of classical mechanics and probabilities, you will be able to distinguish it experimentally from quantum mechanics, because quantum mechanics is different. You don't start with probabilities. You start with probability amplitudes. You have to allow for these non-local correlations. That means without violating our ability to send signals only at the speed of light, or slower, you're going to be able to tell quantum mechanics apart from any other alternative of a more classical kind. Okay, what a remarkable result. I won't really tell you how it's derived, but I encourage you to read about it. 4 lines of algebra. 4 lines of algebra for one of the greatest results of 20th century physics. Okay, have me back to talk to you about it if you don't do it yourself. I'm happy to do that, okay? And here is what the central result is: an inequality of the following type. Bell takes that pair of electrons, okay, in a spin 0 state, but he says, I'm going to measure the first one along one direction, A, and the second one along another direction, okay, C, for some reason I've called it, or B, say. There are 3 directions in his theorem, A, B, and C. So he carries out a measurement of the first one along A, the second one along B, first along B, second along C, etc. And he proved that in every classical theory with local, additional variables, doesn't matter how many you have, there's an inequality between various probabilities. Say the probability to find the first electron with spin up along A, direction A, and second spin up along direction B must meet this kind of inequality, at root arising from the fact that probabilities have to be positive, at most 0. They cannot be negative. This is a general thing, and he showed in quantum mechanics this inequality is violated. Okay, so there's a very sharp difference. Something is true in any version of an augmented classical theory, which would have made Einstein happy, which would have gotten rid of this non-locality in description, and quantum mechanics. And so that made it an experimental question right away. You could test doing an experiment. And this experiment was done beautifully, a version of this, by Alain Aspect, Grangier, and Rogers. And as you know, Aspect got the Nobel Prize, which he shared with 2 other people last year. And here is the data. It's not quite Bell's inequality, but a version of it due to Clauser CHSH. C here is Clauser, who is the second recipient of the Nobel Prize also because of these inequalities, which he formulated. Here's the data. Okay, is some variable having to do with spin orientation. I'm not describing it to you. The hatched region is what is not allowed in any local theory without this kind of non-locality in description. Classically forbidden, therefore. Okay, but it's allowed quantum mechanically. Any such classical theory would have to lie between the bands. The dots are the data. It's 1 sigma error bars. The curve going through the dots is quantum mechanics, okay? And you see how beautifully vindicated quantum mechanics stands, that the data goes through the classically forbidden region is without doubt many sigma effect, and therefore you rule out at one shot all these alternatives, okay? Showing that even though quantum mechanics is weird, strange, can't understand it, it's correct. This is how nature works. Beautiful result, and of course, both Aspect and Clauser were involved in this. Zellinger did other great things, which I won't be able to tell you about today. Okay, quick story, then we'll move on. Aspect has this beautiful set of reminiscences, which are worth reading, for young people especially. He was a very young person when he decided to do the experiments, okay? And he describes how he read Bell's paper and he could think of nothing else, day and night. He said, I have got to test this. It's so foundational. So he came up with his experiment, very ingenious how to test it. And he was in Paris. He took the train up to Geneva. Bell was at CERN to meet Bell. He met Bell and breathlessly for 45 minutes told him the experiment. And he narrates that Bell was absolutely quiet. And at the end of 45 minutes, the first question out of Bell's mouth was, have you got a permanent position? And the reason is, this was so unfashionable. As I said to you, everyone thought, oh, this is some kind of fringe philosophy. Einstein had lost it in his last years, and Bell was worried if this young man embarks on this, he's not going to get a job. Well, luckily, the French have a system where they give to some people tenure at the get-go out of PhDs or so. And so Aspect had a permanent job, and he told that to Bell, and then Bell, of course, encouraged him to do the experiment, which became a Nobel Prize many, many decades later, because it took time. The other reason it took such a long time for the Nobel Prize is people didn't understand the significance of what Bell had shown, what Aspect had demonstrated. and how it's so pivotal for shaping our understanding, not only of the foundations of quantum mechanics, but in fact all of science. Okay, so it's a great story, but if we fast forward, what has happened now after many decades is that people are slowly waking up, okay? If quantum mechanics is truly so different, if it's so different from anything we can achieve using our classical intuition, even allowing for extra variables, extra degrees of freedom, no matter how many, if it's really so different, can we use it to do things we could just never have dreamt of because our thinking is so classical? Okay, this is the thought. This is the thought people have started to seriously explore, and on the face of it, it looks very exciting. It looks like there are many things, in fact, we can hopefully achieve. There is not something I can point to today very concretely. There are only little things, but concretely, in terms of a grand quest which has been proving very difficult that we have achieved, but there's a lot of promise. And in what time remains, I want to share some of that promise with you. Okay? So experiments since then have vindicated quantum mechanics even more beautifully, etc. This kind of entangled property, up, down, minus down, up, is what we call entanglement. And I'll come back to quantifying it a little as we go. Okay, one example which really shook the world up, okay, of how quantum systems could do things which are classically very different was given to us by Peter Shor, who's a computer scientist. And this example also shows the interdisciplinarity of this area. Okay, and you know, there's a very famous problem of great practical importance, many of you know, which has to do with factorizing a composite number into its primes. So for example, if you take 15, it's 5 into 3. Okay, seems simple enough. But as you make the number bigger and bigger, it gets harder and harder in general to find its prime factors. Okay? And this is a well-known difficult problem. And the fact that it's difficult actually is what all the encryption we carry out today to secure credit card transactions, etc., rests on. The RSA encryption at root rests on the fact that this is a difficult problem, and therefore computers of the normal kind we build would take a long time to crack what the prime factors of a complicated number are. In that time, you can complete your credit card transaction securely. Okay, that's roughly the idea. What Peter Shor showed was, if you use the different logic of quantum mechanics, because remember, it is fundamentally a different logic. You're not adding probabilities, okay? You're not adding probabilities. So if you use that different logic with the properties of superposition, etc., you can factorize a number much more efficiently than a classical computer can. How much more efficiently? Okay, let's do it. He, of course, didn't build the quantum computer. He was a theoretical computer scientist. So in terms of algorithms, how much more efficiently? Let's say you're a number, capital N, then the number of digits required to store it would go like log n. For example, if you have a number like 10, you take 2 digits. If you have a number like 100, you would take 3 digits. So log of that, 10 square takes 2 digits, 10 to the 3 takes 3 digits. So the number of digits is a good way to think about how complicated that number is. So let's work with little n. This is the way people do things in this area. The best classical algorithm goes exponentially in n to the 1/3, okay? So it's not quite exponential in n, but you take the third root of n, little n, the number of digits, and you exponentiate it. The important thing is it's exponentially hard, okay? It's exponentially hard. If you have, 14 digits, e to the 14 to the 1/3 is already a big number. Okay, I'll make it 20 to secure my credit card transactions. But the quantum algorithm of Peter Shor, okay, just takes order n square. Okay, it's almost an exponential speed up. Okay, there's a big difference between powers and exponentials, and it's only n square. Okay, and this algorithm just shook up the entire world of theoretical science. I'll tell you, I was working with John Preskill at that time at Caltech. He's now quite a leading figure in this area, and he just disappeared. I couldn't find him for a month, and then finally he showed up. I said, "What happened? I'm looking for you." He said, "Peter Shor wrote this paper. Physics is not going to be what it was before." So I mean, it was a very, very big landmark event. And people said, "Oh my God, if this can happen in number theory, if quantum logic can change our understanding of fundamental algorithms bordering on number theory in such a dramatic way, who knows what else it can do in physics, in chemistry, and so on. And so, it really caused people to sit up. And that's slowly, that momentum is building and driving change. Okay, so this suggested if we can build a quantum computer, okay, then really we'll be able to do amazing things. But of course, I wish I could tell you a little more about this algorithm. It's a really beautiful algorithm. It rests on many beautiful things, but some other time. Okay, now many people are trying to build a quantum computer. Maybe you folks are trying to do it. In TIFR that I know about, Vijay Raghavan is trying to build a quantum computer, putting together quantum bits. And here I got to show you his picture with his dilution fridge. He's a very proud person here. And his qubits, which are based on Josephson junctions. And which has achieved only about 7 or 8 qubits by now put together. The world's leading efforts have, like by IBM, have 433 qubits, seem to be very far along. But the interesting thing is, none of them is actually a workable model today. And the reason is, it's one thing to put qubits together, another thing to protect them against errors. Okay, errors can accumulate in the quantum world more rapidly than the digital world of classical computing. You have to work hard to make sure that your computing is error-free, what's called fault-tolerant. And none of the architectures today, even though they may have 433 qubits or whatever, can quite successfully do error correction. So I think the game is wide open. Okay, and it's wide open vis-a-vis what basic units of computing we'll use, what kind of gates, how we'll put them together, what kinds of architecture, what kinds of algorithms. So there's computer science, there's physics, there's putting together things using material properties, and it's a wide open game for really very important contributions to be made into the future. Okay, but how much time do I have? 5 minutes. Okay, good, excellent. So we're not there yet. There are many challenges. And interestingly, if you ask how, I can't go into how you correct errors in quantum systems. Very different from, quantum systems are more analog, because if you know about spins, you know spins can precess. Right? For example, this is the key to NMR and so on. So spins can precess, they are more like analog degrees of freedom, and you have to try and correct for errors of an analog system as opposed to digital system, which is 0 or 1. It's much easier to correct errors there. So there's a big issue. But again, the key insights have to do with entanglement. And the key insights are, use the weirdness of quantum mechanics to fight the errors of quantum systems. And it's a beautiful theory which has been well developed. And at least theoretically, there is no obstacle today to being able to build a good high-performance quantum computer. Of course, whether we can actually realize it is another story. Okay, so many challenges remain, but I think the future is wide open. Meanwhile, as you all know here at QTF, I'm sure there's lots to do in other ways in exploring the ideas of quantum mechanics and putting them to use in building devices, measuring devices which can do much better sensing of small physical changes, what's called metrology, quantum sensing. Quantum communication is another very, very important area. A lot of work is going on where, again, you put the essential nature of quantum systems to use. If you observe a quantum system, you disturb it in an intrinsic way. This is part of Heisenberg's principle of uncertainty. And you use it to make eavesdropping very difficult, or at least to be able to detect eavesdropping in quantum communication. So there's a lot going on in these areas. I'm sure you're aware of them. And probably the progress in tangible terms will come more in these areas in the near future, but also maybe impact our understanding of how to do grand things like building sizable scale quantum computers. I want to tell you about a very small thing which we were involved in TIFR, just to give you an idea of how easy it is to kind of make an impact. You know, we were approached by the DRDO to help set up a DRDO Young Scientists quantum lab. And there were these engineers who weren't trained in quantum mechanics, and you know, we had to do interesting things with them. So what do you do with them? So we said, okay, let's start with the superposition principle. Okay, we'll come to entanglement next. Can we use the superposition principle for something interesting? Okay. And turned out we could do something very simple but very useful. You know, here's a very interesting question. Can you have true randomness in nature? Now, in the classical world, as I was trying to say, the answer may be no, right? If you keep track of everything, you don't have true randomness. But in quantum mechanics, you have true randomness. If you measure an electron which is in a superposition, it'll either come up plus or minus. It'll be truly random. And the idea was, can we use this kind of randomness? In this case, very much like Young's experiment, you split a beam. It's either gone through the first slit or the second. Those are the two states. Can you put it to use to actually build a random number generator? And very simple ideas, just randomness of path superposition. Using that, these people, the DRDO scientists along with help, could build a very nice random number generator. It meets all the tests for true randomness, the most stringent ones. It operates at speeds which are comparable to the best devices. It's been commercialized. It's been inducted. You see here with the Honorable Minister of Defense. It's been now accepted for being inducted into the armed forces. Okay, such a simple idea. Just use superposition to generate true randomness, already being put to use. So there are many interesting things you can do using simple ideas if we internalize the workings of quantum mechanics. Okay, and I think this is the realization that people are slowly getting, that quantum properties are a kind of resource. Let's use them to do things otherwise very hard to achieve. Okay, very, very quickly, one sentence or two. The kind of work, I'm a theorist, don't get to work directly with building equipment, soldering stuff, and so on. But the question we asked is, okay, since entanglement is so important, how do you quantify it precisely? For that 2-electron state, it's clear they are entangled, up, down, minus, down, up. But okay, more precisely, how do you do it? And it turns out, you know, it's quite a challenge. It's quite a challenge for the kind of theories which actually occur in nature. One example of this is, of course, electromagnetism. But the property I'm describing is true more generally for gauge theories of various types. Electromagnetism is an example. The strong interactions, the weak interactions are other examples. Even gravity is an example. And there are many examples which arise in condensed matter physics as emergent gauge theories. And it turns out to be very subtle due to a property in gauge theories I wish I could discuss with you, which is called the Aharonov-Bohm effect. Again, a quantum property. Okay, which doesn't have a classical analog. This makes it very difficult to isolate locally the degrees of freedom, okay, of a gauge theory. You know, for the two spins, at least we could say first spin is here, the other is in Andromeda. Now, how entangled are they? In gauge theories, it's even hard to say what are the local degrees of freedom. If that's hard to do, how can you say how entangled are two sets of degrees of freedom, one here and the other in Andromeda? This was the kind of question, but we gave a very precise answer. And we also explained what it means operationally in terms of, you could say, finally, I'm only interested in doing Bell's experiment, okay? How many Bell pairs can I get out? How many pairs of up-down spins in a correlated way can I get out? That's my operational measure of entanglement. So we could codify everything in terms of that operational measure. So we have today, summary, a very precise theoretical understanding of what entanglement is. You give me a system, we can say how much entanglement there is by way of this quantum resource, and then you can take that resource, convert it into Bell's electron pairs, some other system, correlated photon pairs, whatever you like, and put it to use for, you know, doing the kinds of things quantum systems allow you to do. Okay, so let me come to the end of the talk. I hope I've been able to convey some of this excitement to you, which I really feel in my heart. Despite a century of intensive study, we are only slowly coming to grips. This is the main thing I want to tell all of you young people, okay? Only slowly coming to grips with the true weirdness of quantum mechanics. And what we are learning promises to change all of science in the decades to come. Entanglement is a key property. I tried to at least intuitively explain it. Thought to be very strange, now understood to be intrinsic and extremely powerful, present in quantum systems. Using entanglement, we hope to build workable quantum computers, find new ways of measurement which are much more sensitive. A new frontier is literally opening up in front of our eyes, and I think there are many exciting discoveries to be made. I hope you will all join in the fun in the days to come. Since I'm a failed scientific administrator, let me mention one thing. These postscripts are hard to not give. You all know this, but it's worth mentioning here just in terms of opportunities. Here's the Honorable Finance Minister in the 2020 budget declaring a national mission for 8,000 crores, okay? 8,000 crores, quantum technologies and applications. I'm sure you all know about it at QTF. But this is a huge, too big an amount for the country to absorb. But even if it's scaled down, it's a tremendous opportunity. And the DPR, I'm told, is getting ready now in the final stages. So I think it's such a great opportunity with your hub located here for you to participate in a truly significant way in these great discoveries that lie ahead. Thank you very much for your time.
Thank you, Professor. That was indeed thought-provoking, informative, but also very intriguing and exciting, I'm sure, for all of us. I would invite our director to please present the token of appreciation to our chief guest. Thank you again, sir, for gracing this day with your presence. I would request both of you to please remain on stage because we'll shortly commence with the award distribution ceremony.
Students are an integral part of the IISER community who have propelled this institute towards excellence through their talents and perseverance. As an accolade to students for their exceptional academic performance, we will now begin with the awards for academic excellence. I request Dr. Gayatri Panankar to commence the award ceremony.
Good afternoon, everyone. So the Academic Excellence Awards are based on the highest semester GPA for the semesters 1 to 4. And for the semesters 5 to 8, the awards are based on the highest annual GPA. The Academic Excellence Awards for Semester 1 for the BSMS Batch 2022 are awarded to 4 students, all of whom have a semester GPA of 9.8 and 6 A+ grades. So I invite Dheeraj Deshpande, Jagadish Parameswaran, Shubhan Ramesh Gupta, and Vivek Rajesh Joshi to collect the awards. Jagadish Parameswaran, Shubhan Ramesh Gupta, Vivek Rajesh Joshi, the CNR Rao Education Foundation Prize for Semester 1 for the year 2021 goes to Komban Subhash Christopher, who achieved an SGPA of 9.7. The Academic Excellence Awards for Semester 2 is for Mugdha Ashirwad Tate with an SGPA of 9.8. The Academic Excellence Awards for Semester 3 is also for Mugdha, along with Sujita Suresh, both of whom have got an SGPA of 9.9 with a total number of A+ grades of 6. Sujita Suresh. There are 3 students sharing the prize for semester 4. All of them have attained a SGPA of 9.9 with 7 A+ grades. So these are Rick Sarkar, Srivalsa S. Kripat, Atharva Abhichit Valmi, for semester 5 and 6, we have Shah Varun Kaushal, who has got an annual GPA of 9.7. He is not here today. The next one is for semesters 7 and 8. So this goes to Mihir Neve, who has got an annual GPA of 9.8 with a total of 11 A+ grades. The next awards are for the integrated PhD batch of 2022. So these are the students who have completed 4 semesters of coursework, and the student with the highest CGPA in each discipline is considered for the award. In biology, we have Ojal Saharan with a CGPA of 9. In chemistry, Bikirna Roy with a CGPA of 8.8. For mathematics, we have Kaustubh Mandal with a CGPA of 9.3, and he is not here today. In physics, we have KS Dhruva with a CGPA of 8.7. Thank you all, and congratulations to all the students.
Thank you, ma'am. Many congratulations to all the awardees. A teacher affects eternity. They can never tell where their influence stops. We cannot emphasize enough the importance of our faculty members and the instrumental and at times pivotal role they play in our lives. In an effort to appreciate all that they have done and continue doing, I would like to invite Professor Pinaki Talukdar to present the Certificate of Appreciation to the faculties.
Good afternoon. So we have 9 faculty members from different disciplines who are going to receive the Certificate of Appreciation for their teaching. So first this appreciation is based on the feedback received from the students and the consistency of their teaching in last 2 to 3 years, and also excellent students' feedback that they have received. So first I call upon stage Dr. Gayatri Panangat. She is Associate Professor at the Biology Department. And just to appreciate how students one of the students have given her feedback, I will make that statement here, that she explains the concepts in a way that is easy to understand and is always available for after the class discussions, very interactive and interesting classes. So next I call up on stage Professor Jayakannan. who is a professor in the Department of Chemistry. In his teaching course, one student has given a remarkable feedback saying, absolutely energetic teaching, knows his stuff so clearly and brings the same clearance in his teaching. The only reason I come to the class at 9 a.m. every day for his teaching. So next I call up on stage Dr. Angshuman Nag. So he is an associate professor at the Department of Chemistry. So in his class, a student has given an excellent feedback saying, very creative and experimental teacher. He connected the phenomenon with physical stuff which were visible to us. He demonstrated many physical experiments to us live in the class, which is every one of us enjoyed. Meanwhile, we also learned something from him. Next, I call upon stage Dr. Srijit GJ, who is associate professor in the Department of Physics. So in his class, one student has given feedback saying one of the best courses so far. Everything was made so clear in the class. Completed Griffith electrodynamics with a reasonable pace and complete understanding. Exams are hard, but that makes me study more and appreciate electrodynamics properly. So next is Professor Sudarshan Anand. He is a faculty member in physics. He is not here, I think, today. So one feedback for him was the course was almost perfect. The ease with which the instructor taught the concepts felt unreal. The exams was tough and challenging, yet not complicated. Next is Professor Anupam Singh from Mathematics Department. Yeah, he's here. So again, I will present one student's feedback here. This was an excellent course. Going into the course, I was worried that it would be a bit too abstract for me, and I would struggle a bit, but on the contrary, I kind of enjoyed the abstractness and the beauty of the group theory. The lectures were super easy to follow, and the course structure was well designed. So next I call up on stage Dr. Kaninika Sinha, who is an associate professor at the Department of Mathematics. So in her, one of the courses, a student has stated, fabulous, a truly transformative course for me, set me down the path of exploring much more maths in the future. Extremely complicated concepts were communicated in a clear, simple, and elegant manner. The content was very interesting. The problem sets were challenging in a good way. So next I call up on stage Dr. Arjun Datta. He is an assistant professor in the ECS department. I think he's not here. So I will again present one of the students' feedback. The course was very interesting in terms of variety and diversity of topics taught and widespread applications of physical principles on Earth. The problem sets helped clear and lots of misconceptions. And I call the last faculty, Dr. Pooja Shancheti. So she is an assistant professor at the Department of Humanities and Social Sciences. A student has given a remark, very enthusiastic. I don't know how time flies, accepting of diversity in thought and opinion, open discussions, and thought-provoking conversations, great classes. So I thank all the teachers who have received the Certificate of Appreciation in this year. Thank you.
So I think the key is to set tough exams and tough courses, and you'll get the best teaching award.
Thank you, Professor Talukdar. Now, anything is possible when you have the right people there to support you. And to say that our staff members have been a monumental support system is an understatement. Thus, I would like to invite the Registrar, Colonel G. Rajashekhar, to present the Certificate of Appreciation for the staff.
Good afternoon, everyone. So it's my privilege to announce the Best Employee Awards for the non-teaching and also for the outsourcing staff. The first on the list is Salim Sheikh, who heads the purchase team. Though the funds have been coming very erratically in the last financial year, but we have a mandate from Government of India to make everything zero in the midnight of 31st March. And it is very difficult to do that thing for capital procurement. And he has ensured that, and there has been targets he has achieved, both for the grant aid which he received from the Government of India and also from the HIFA loans. Salim Sheikh. Next is technical assistant from the Earth and Climate Science Department. This is to Vikrant Bartake for his contribution in handling the state-of-art XRF instrument. Next is from the Accounts Department, Priyanka Chavan. This is for handling all the medical claims and the queries to all the faculty members and the other staff of the institute and clearing of all the medical bills. Next is the Naveen technical assistant from the IT department for its contribution to cater to all the IT needs of the institute. Next is Shakti Tiwari from the Administration Department for her contribution towards the handling all the recruitment related issues of the non-teaching staff. Aparna Shimpi from Stores and Purchase for her contribution towards the processing of all the purchase indents. Nikhil Khakde from the, he has been recommended from the PTO's Research and Communications for his outstanding work along with Shanti for helping her in the preparation of the annual report. Next is Anil Pratham Shetty from Technical Assistance from the Physics Department for his excellent contribution in maintaining FEACM in the Department of the Physics. Next is Ankish Tirpude, Technical Assistant from Science Activity Department, for handling all the teacher training programs and the demonstrations associated with this to all the students. Next is Hari Prasad Dande, Technical Officer from the Department of Biology, for his excellent contribution in the maintenance of all the instruments of the department. Next is Mrs. Rupali Yadav, Technical Assistant from Biology. This is for her contribution in managing all the Indians of the department. Next is Ganesh Dimbar from Laboratory Assistant from the Department of Chemistry, for handling all the purchase related work of the Chemistry Department. Suvarna Bhardwaj from Mathematics, for handling all the work related, office work related in the related work in the Department of Mathematics. Next is Sneha Chordia. She is from the academic department, and she has been managing all the PhD and the MS thesis submissions and evaluations very efficiently. Alok Mishra, again from the academics department, and he has been single-handedly managing the admission process for the PhD, integrated PhD, and the MSc programs. And next is Ketan Kakte. He is from the engineering department, and he is the one who processes all the contract bills. Now comes the outsourced staff. These are the housekeeping and the security from the engineering. First is Nazia Faruqi. She is the PA to the Dean's office. She has been nominated by Professor Santanam for her outstanding work. So our security staff, round the clock, they man the institute, and also in the event of any untoward incidents, they immediately get into action. So Mr. Rahul Divekar, security guard. Somnath Sate is from the housekeeping. Ramesh Dharwadkar is the driver. Mahesh Shelar, electrician. Sandeep Mistry, carpenter. The next awards have been recommended by Professor Deepak Barua, the chairperson of the Landscape Committee, Mr. Ganesh Sawant, gardener. Santosh Jadhav, gardener. The next awards have been recommended by Professor R.G. Bhatt. He is the chairperson of the dining committee, and they are working for both the V Square Services and Shiv Sagar. And first is Dilaram Sharma from V Square Services. Krishna Pujari, Shiv Sagar. And the last person is Vijay R. Patil. He's an office assistant from the grant section, and probably I think he's not here. And with that, I come to the end of the Best Employee Awards for the non-teaching and the outsourced staff. Thank you very much.
Thank you, sir. Thank you, Professor Trivedi. Thank you, Professor Jayant. Many congratulations again to all the recipients. We are extremely grateful for all your services. Moving on, Kalpa, IISER Pune students' media body, aims to ensure that no voice is unheard and all of us remain well informed of the happenings around campus. Kalpa magazine is one of the ways in which this is achieved. I would now like to invite Professor Jayant Udgaonkar, Professor Sandeep, and our Chief Editing Manager of Kalpa, Manav, to release the latest edition of Kalpa magazine.
Thank you for gracing us with your presence. You can, yeah. Thank you. With this, we are now approaching the end of the ceremony. I would like to invite the Dean Academics, Dr. Girish Ratnaparki, to deliver the vote of thanks.
Pretty much good afternoon, everybody. On behalf of the Director IISER, I would first of all like to again thank Professor Trivedi for coming and giving a very spectacular seminar for our Foundation Day. I'd like to thank all our distinguished guests who have taken the trouble to come and celebrate our 13th Foundation Day with the rest of the community. Many congratulations to the staff, the students, and the faculty for the recognition that they have got today. I would thank everybody who has been involved in setting up this Foundation Day. And with that, we break for lunch. Thank you.